Hello everyone. Today I'm gonna be talking about the recent modifications that I made to the PulseCore project. So I basically integrated the gRPC into the project by removing the Bayer TCP communication protocol from the project. So basically, I integrated the gRPC and containerized the client and the server side of the messaging part of the project. So first, let's dive into the proto folder. That is the heart of our project. So proto folder defines actually the set of functions required for communicating between client and server. So it defines the client stub that is crucial for clients to communicate forward messages to the central server. Then it defines the functions for broadcasting messages, and so on and so forth. Here in the message proto, you define your own message types. So message requests. So you define your service RPC functions that you will be using integrating with your Golang based system. So here we define broadcast message that is required for broadcasting messages from the server, from the host, to all the other connected clients. Then send heartbeat. So I defined it for checking the liveness of every client, whether uh, client is still connected or not. If the heartbeat is not responding within a certain time frame, that means that it's disconnected. Then I just delete the client from the set of clients connected to the server. So we also have like register client RPC function that registers client. It's this function basically is invoked by a client once it's running, once it's up and running, and it's the RPC call is made to the server to register it into the gRPC cluster, say. Then receive message from server. So this function is needed for handling uh, arrival of messages broadcasted by the central server. So basically, when you send a message from one client, the message is sent to the central server, and the central server then forwards this message to all the other clients in the network. So this received message from server identifies whether a message is received or not, and returns an appropriate message if it's received. So all the other functions, the definitions, message types are in the message proto folder, file. So basically, how you run it, you should run a command, which is like proto you define. So it's basically I think in the readme. Yeah, it's this one. So basically, define go out. So it can be proto. So where the generated Go files will be saved in. The opt path we can also set to proto, gRPC also to proto, the gRPC opt also to proto. So basically, once you run this command should generate these two files. These two files contain the implementation and of the functions and definitions defined in the message proto. For example, let's say register client. I think it's here. Register client. No, it's in the gRPC side. Yeah. So it's basically the implementation is in the game service client, which is this game service client. So we basically define it in here, register client, define it in here. So it's basically taking the register, so the input, so the signal, let's say, of client and registers it in the network. And all the other implementations also, yeah, in here, such as receive message and all the others. So yeah, so this is the proto. So let's dive into the actual simulation simulation of what I've been working on this week. So basically, to run the project, you first need to pull the Redis image, and then you should run it in a container. So you can have several Redis images. When I was creating the architecture, I was thinking about like one-to-one association between server and Redis. So Redis is basically needed for room handling. So short story less, if you have one server, you should have like one assigned Redis database that will contain all the rooms and the players in the rooms and will be used for room management. You can use the same Redis database for two servers, and the two servers will be sharing the same room handler. So it's a nice idea that I'll be working on probably later. So it comes in handy if you want to implement a system with like distributed databases. So if one just goes off, you can like seamlessly send on all the loads from the first server that the players were playing on to the second one, the third one, and to the fourth one by making sure that the Redis database remains the same. Basically, by that you make sure that the game states they remain the same and players can play seamlessly. There's another issue that needs to be tackled, which is implementation of such a system that will flawlessly forward the control from one database to the other. So yeah, so I think I set up the Redis. Let me check. So Redis is up and running. The server is also cool. So the second one is setting up the server container. You can basically run this command. So I'll just explain what's going on here. So we basically define a server address. You pass server addr, which is a service address, a server address. And here I set up the IP address as 0000, which means that the server can accept connections and requests from any other external IPs. So so basically means that once it's deployed in a container, it can accept requests from external IPs to the host IP of a container. So here you set up a port. It can be any port in the range of 0 till 65,000 and something. So it's basically 2 to the power of 15, the range of IPs. So yeah, you pass the Redis address basically. So yeah, server address is the address that the server will be running on. The Redis address means it's a container that our Redis is running on. So we basically specify the name of a container that we specified and run. So it's basically this name. So when you specify the name of a container inside a Redis other parameter, this container name will be converted into the external IP of the container of the Redis container. So basically, so far it's working this way, and you also need to put the port of the container. And the network should specify the Docker network. Make sure that all services are working on the same network. So in this specific example, I use PulseCore network. Otherwise, the containers won't be able to communicate with each other. So basically, you're disrupt the gRPC communication from clients to servers. You specify the port. The port can be external, can be set up to 1, 2, 3, 4, 5, whatever, and the internal is 1, 2, 3, 4, 5. It's basically this this port in here. So the port inside on the port. So basically, the first one is the port of the server router. The second one is the internal one. So name, you just specify the name of container and then just call the image. Yep. So it's working, right? Yes. Let's double check its status. So it's up and running. Cool. So now this is the moment of truth. We run our first client. Let's make sure. All right. No clients running. Let's open up some terminals. I'll run two clients to show you how messaging and room handling actually works. This so basically this command is a little bit wrong. So basically you will not be able to run your client. I'll update the README. So I fixed the command. So it's basically this. So you specify the network. As you see, it's working on the same network as the server, and Red is actually also working on the same Pulse network bridge on the network bridge. So specify D to make sure that the client is working on the background, but we don't need it because actually I want to show you how the simulate. I want to simulate how the client is working. So it's basically put it to make sure that the terminal is assigned to the container. Otherwise the buffer will not be able to have a specified buffer assigned to it. So it's basically in here. In the client, you call buff.io new reader operating system std input. So if you don't set the it argument, it won't be running because there will be no std in assigned to the reader. So it's basically so it will be running infinitely in an infinite loop by consuming your CPU till the moment your CPU just dies. If you don't just turn it off, I'm just kidding. It will be handled by the Docker. Docker will uh, kill the process. So yeah. So you specify the port. Basically, you can specify the external and internal ports, but I would rather prefer running this way. So this way, uh, the external port will be picked up from the range. An available port will be picked up from the range, and the internal port will be assigned dynamically. So you name your server. So you name the server that is running that you want to connect your client to, the port of the server, and the server of the Redis, because each client communicates with Redis also. It's basically a common channel for servers and clients to communicate. So let's run it. Let's run and see. So let's give it a name. PulseCore client with same route. Let's run it. It's taking a bit of time. So yeah, so client is working. So we connected to we assigned the port to the client. We connected the client to the server, and we connected to Redis. So basically, can list rooms. So there are no rooms. Let's run the second client and simulate the behavior. Let's take the same command. Right here, just rename it. Uh, Name actually is non-unique. You can basically set up whatever name you want. The uniqueness of a player is identified by its RPC address. So basically, its RPC address is its like primary key, if I may call it this way. So let's name it in some foolish way. Let's make it just simple client 123. Make sure the PulseCore everything is correct. The server, the Redis server. Let's give it a name. Let's give a name for the container. Client 123. Let's run it. You can also track the clients on the terminal. Okay, it's connected. Cool. Now we can check the containers. So yeah, so it's basically kind of messing here because like for every IP, so we basically specified like 0000 to the client. So it's basically it will be like arranging a set of available IPs for the client. So you see the PulseCore client. So names. So where is the other one? PulseCore client. Hmm. Anyways, so I'll need to probably work on that. So yeah, let's pick up the first option, which is send message. Let's say, hey, the message is received in here. So you received message from another client. So actually, that was the RPC call. So basically, we send the message to the stop of the client to the server that is running on the Docker container. We can check it. Docker PS. Let's find a server. So the server should be the first one. No, the server. All right. Docker inspect. Let's inspect it. That's Redis. So we can basically check the server from the Docker desktop. So you see, the message was received and the server broadcasted it to all the other clients. Let's send another message. It's actually very fast. And cause the gRPC uses the TCP connection, the order of packets is defined. So basically, you are just 100% sure that all the messages, all the function calls you make from clients deliver to all those clients in order. So let's create a room. Let's call it first room. Now we can list the rooms in both the clients. You can join a room. Once you're once you create a room, you are automatically joined to it. You can view the current room state. So it's basically server ID is not specified. Is actually it seems like a bug, but basically it has to have the server ID assigned to it in the key. So status is available. Properties. Properties are the properties or the custom properties set up by a user. Basically, like uh, client will be able to set up any property to the room from Unity, Unreal Engine SDKs, or any other SDKs, or from Bayer client, Golang client container. Date created, room ID, host ID. Host ID is actually the port of the host. So it's actually the port of the client. Maximum players 10. You can also set it like to any other value. Current players 1 and players in room. So this is what I was talking about. As you can see, so in this room there is only one player, and its identifier is the following. So this thing on the left side of the column, with the semicolon, is the address, is the RPC address of the player, of the client. So this is the exactly the same host ID. So this is the RPC address, and this is the name. Basically, this RPC address is the identifier for every player in the room. So this way, server can handle the deletion of clients from server from rooms once they're inactive. So basically, based on that. So the other one, the key on the right side is just a name, client name. As I said, it's non-unique. So basically here we can try to join a room. We can type with its ID, which is 1 7. Now there is two players. Two players. We can try to disconnect. Just terminate the terminal. Now as you can see, it was quickly set up back to the other value. The players in the room was modified to the current client. So basically we leave the room. We see that there are no rooms anymore because the client just because the server just immediately determines that the room didn't have any players in it, and it immediately deleted it. It's actually in here, and the server.go, the monitor room states. It's basically in here. Checks the current players. We get the key, room key from the current room. So we get the current players properties value from the room. We iterate through every room in ticker. So basically in 1 second, you can actually change the value. So it also has some drawbacks and benefits, actually the advantages. So if the number of ticks is pretty high, you can be sure that there will be no load on the server. If it's too low, so it's like 1 second or maybe less, the system will be working pretty fast because they'll be fetching the data in 1 second. Actually, it's not a big problem for Redis. It's doing it just uh, like very fast, but still there can be some cons such as server overload. So basically, we'll have to vertically scale up the server to make sure that everything works properly. But nowadays, there are a lot of solutions for that, such as AWS, GCP. So basically, it's not a huge issue. So next, we can list the rooms. I showed you the current room, join room, create. Yeah. So this how's working. So if we terminate the clients, the clients will be deactivated. That's the first one. So Client will be deactivated this way. So that's actually a pretty flexible solution. If you want to have like a lot of players, manage them, manage their sessions, you can basically set up all this Docker thing. You can wrap it up in Kubernetes. You can deploy it in AWS or GCP or any other sustainable and uh, proper server provider, and make sure that like the clients, the servers, the Redis servers, everything is orchestrated, scaled up, down. It's pretty cool. So later this week, I'll try to uh, create a Kubernetes wrapper for the Docker system of the project and show you how it works. And eventually, I want to deploy it in one of the servers in AWS. So yeah. So basically, Another advantage is that you can wrap it up in Kubernetes. You can deploy it in several regions, server regions, and in any cloud, and handle each player in each of the regions separately. Also, the providers such as AWS, GCP, and others, they provide a feature called fleet management. Basically, like for every region, there will be a set of services running as separate Kubernetes pods that will be in charge of handling and tracking the states of the servers inside of the region. There can be multiple servers. As I said initially, basically you can deploy multiple servers and use like systems like sharding, methods like sharding for distributing the clients between each one of those by making sure that they work actually as if they were the only one server. So yeah, this was the introduction. You can go to the GitHub repository. I'll update the README page. I'll update the commands. You can clone it. You can run it. You can modify it. You can fork it. You can create PRs for that. So yeah. So see you in the other series.